All right, so this one here just shows the kind of massaging you have to do on the data, and it also helps point out how much intelligence is not in the machine, but is added by the human. So we're going to use this California housing data. So let me bring this in and let's see how it works. Wonder if I can I guess I'll have to log in again probably, but simplest way to like clean up the environment that I know of. Okay. All right, new notebook. Yes, okay. And here's the package versions we're going to use. sklearn is the main one this time. And this happens, I delete, terminate all other sessions. Okay. All right. You lie. Terminate, no active sessions. You're going to stop complaining? Okay, good. All right, and so now we're going to get the data we're going to work with, which is housing data. This is, I think, from some government agency. It's data about the price of houses in California, and I think it's from the 90s because the houses prices are pretty low. So here's what you have: latitude, longitude, things like median age, and you have the house value here, which is what we're going to try to predict from this other data. And notice all of them are floating point numbers except for one thing called ocean proximity, which is an object. So this demonstrates the problems with handling real data. Real data is pretty rude, not formatted correctly, and in strange forms that are difficult for the machine to handle. So if you look at the first few rows with head, you'll see what the data looks like. Latitude and longitude are fine. Here's the age, total rooms, and here's this ocean proximity is the string near bay. So you can get categories and counts. A very powerful thing. I used to do this kind of stuff for years. Working under contract with the Federal Trade Commission, I would have seized data from people that had been sued, and I would have to massage it enough to where we could figure out how to write checks from it. So here's what this thing has, these strings, and here's the probability. So it's not a number, it's not anything close to a number. All right. And then you can have statistics. Describe will show you the standard deviation and average of these various numbers. And this points out things like you have latitude and longitude are like a minus 119 plus 35. The age is like 28. So all these numbers are totally different scales. And as we're going to see in more detail later, okay, I can't operate this thing. All right. This would be telling it that this number is like 10 times more important than that number because it's bigger. And that's not what you want. So the scale matters. Anyway, but the first thing is to decide which parameters are valuable, and for that, a histogram will get us started. All right, so this will give us histograms showing how things are distributed. So longitude and latitude, I have two peaks, of course, because there's a bunch of houses near San Francisco and a bunch of houses near LA, and not much of anything else in California. The median age seems to have a strange distribution, not a simple peak at all. Rooms, bedrooms, and populations, and all the rest seem like reasonable poissons, but notice this, the housing value goes up to 500,000, and then there's a huge spike there. So apparently 500,000 is the largest available number, and people just put that in when it was more than 500,000. So the data is not accurate. This is not really 500,000. I don't believe there's a huge spike at 500,000. So the data has strange biases and errors, which you have to remove if you want your machine learning model to actually learn the underlying trend and not the specifics of this data. And that's a human judgment, especially if you consider situations like polling to see who's going to win an election. You have to massage and adjust the numbers to try to compensate for what you imagine the errors to be, and it's a pretty fraught process. But that's the way you are. So here, we're going to make a training set and a test set out of the data. And here, we can talk about biased sampling, and this is a problem. So if you have something that depends on the sex of someone, like a medical condition or something, females are 51% of the human race. And so a random sampling of humans, if the real population is 51%, then of course the most likely thing is your random sample will be 51%. But you have a pretty good chance of your sample being 53% or 55% females, and therefore you would have a non-representative sample, and learning from that sample would not be learning the actual tendency of the underlying population. So instead of doing random sampling, which has a chance of being wrong, you do stratified sampling. Now here, it turns out that the income category is a strong predictor of the price of houses, which would seem obvious. If you want to sell an expensive house, you have to sell it in the area where the rich people live. So we don't want to have a random sampling of income category. Instead, we're going to make a stratified sample. So first, you make bins of income here. So here's the borders between them, 0, 1.5, 3, 4.5, and 6, and whatever unit the income is put in. And now here's the distribution of incomes of various. Now you make 5 bins of income, and now instead of doing random sampling, you do random sampling of the data in each bin separately. So you make sure to get the correct relative proportion of each of those bins, instead of a truly random sampling, which would be biased, or to have a high chance of being biased. So now in the training set, I have 35% category 3 and 31% category 2, and I make sure the same thing is true of my test set. So it is random, but only random within each bin. And the total number of samples I draw from each bin is chosen to make sure I do not bias the population in each bin relative to each other. All right, so then you remove a column. All right, then you can visualize the data. This is pretty amazing. I think I'll just look at the examples here. So you can plot it out and see the data, but the problem is in the densely populated areas of Los Angeles and San Francisco, the dots are so thick you just get solid color, so you're not really seeing the data. So it'd be better to use transparent dots, which more accurately tell you where the density is. And if you include population and price, you can even have nice graphs like this where the color tells you the median house value, and the population is determined by the size of the dots. So you can have a lot of this information. All right, but for most important thing for us though is correlations, and this introduces something really important in machine learning, which is you can make synthetic data from the original data that turns out to be better. So here, I'm going to take median house value. I'm going to create a new thing called median house value. Let me get this one right. Median house value, total rooms, and median age. Let me skip that. Here, my scatter plots are going to tell me. All right, let's get down to this one. There. I just replaced this one. All right. All right. Now what you see here is correlation of things, and I've got median house value, which is what we're trying to predict. And you can see median house value is strongly correlated with median income. Like I said, if the income goes up, the house value goes up, and there's a trend here. You can see a clear trend. There's not much trend here and not much trend here. So that seems really powerful, really important. Here it is again, median income to median house value, another view of the same thing. These scatter plots let you see which of the variables are most predictive of the thing you're trying to predict. So here, we're going to see them. If you look at them in more detail, then you will also see other things you have to fix about this data. If I can get to the right window. There we go. All right, if you look at the median house value as a function of median income, the main finding is the trend, but here's that problem you saw before, far too much data rammed up at $500,000 when that's cannot really be reflective of the underlying, and you can also see 4.5 million, 3.5 million, and apparently there are other quantizations. People have apparently rounded off the house value in some of this data, so this data is really not representative of the underlying population. And this is the kind of judgment call a human has to make It's pretty disturbing. It's not really like the kind of science where you take the data and fit it with a mathematical model. You have to massage the data and remove the ones you don't like and come up with arguments about it. So that's a little disturbing to me as a hard scientist used to be doing. And this is the one that really caught my attention. You can make new fields from the existing fields, and they turn out to be more valuable than the existing fields alone. Because remember, these are not independent measurements. They're just measurements of real human behavior. They might depend on each other in various ways. So you can, I should see a correlation matrix. Let me go to my instructions here. Yeah, here, that's right. It's the right thing. So now I can see the, I'm not seeing the correlation value here. I wonder if they changed my version number again. I should see median house value. Oh, it's just labeled wrong. Oh, I see. Okay. It's formatted differently, but here's, I think, the point. Yes, 68% prediction. Okay, this is the strongest these are correlation coefficients. So 1 means perfect ability to predict, 0 means no ability to predict. And so if you know the income, you have a very high chance of predicting a house value from it. 68% correlation. So that, you've seen that before. But these other things, 15%, 13%, and almost 0, those are the predictive things. So this is the most important predictor. These 3 things here have some predictive value, and the rest is pretty much trash, not actually contributing anything useful. All right, but you can make synthetic fields that will do even better and attribute combinations. And one of them that had a very high combination was minus a quarter. I think we'll see it at the bottom of the list. Yeah, the bedrooms ratio combined by 2 others. And the bedrooms ratio is total number of bedrooms divided by total number of rooms. So the houses with more bedrooms cost more. Anyway, so, and this is a thing that's going to come up again and again. You can take the data and make new data from it, and the new data is often extremely useful. And as we're going to see later on, you can make things into straight lines that aren't straight lines, something scientists know. If you have something that's not a straight line, you can often make it a straight line by plotting it on log paper or other kinds of paper. So transforming the data to turn it into a straight line is often quite helpful here. So that's the input data. Let me stop this recording.